Mars, often called the Red Planet, has fascinated humankind for millennia. Its reddish glow in the night sky has sparked curiosity, wonder, and myth. This journey with Mars begins with the ancient civilizations, which recognized Mars as a unique object in the sky, different from the stars or the moon. For these early observers, Mars was more than a planet, it was a symbol, a celestial mystery. The ancient Babylonians, one of the earliest civilizations to record their observations, noticed Mars as early as the 2nd millennium BCE. They referred to it as Nergal, after their god of war and plague, due to its fiery red color. The Babylonians meticulously tracked Mars' movements across the sky, contributing some of the earliest known records of planetary observation. In ancient Greece, the association with war continued. The Greeks named Mars after their god of war, Ares. They noted Mars' wandering path through the sky, a phenomenon that distinguishes planets from stars. Mars' retrograde motion, an apparent reversal in its course, was especially puzzling, and it played a role in the Greeks' evolving understanding of the cosmos. Similarly, the Romans, who adapted much of Greek culture and mythology, also named the planet after their god of war, Mars. This name has endured and remains today, reflecting both the Roman heritage and the planet's captivating, blood-red appearance. During the Middle Ages, Mars continued to captivate astronomers and philosophers. Islamic scholars like al-Battani, al-Batinius, and al-Sufi refined astronomical techniques, improving the calculations of Mars' position. These medieval astronomers made key advances in observational astronomy that would influence later European scientists. By the Renaissance, as Europe experienced a revival in science and art, Mars became a key object of study. The 16th-century astronomer Nicholas Copernicus introduced the heliocentric model of the solar system, which placed the Sun, not Earth, at the center of the universe. This revolutionary idea suggested that Mars, like Earth, orbited the Sun, reshaping humanity's understanding of our place in the cosmos. The renowned Danish astronomer Tycho Brahe took Mars observation to new heights in the late 16th century. Although he used only the naked eye, telescopes hadn't been invented yet, Brahe's meticulous measurements of Mars' position were groundbreaking. His data allowed his assistant, Johannes Kepler, to develop the laws of planetary motion in the early 17th century. These laws, which describe how planets orbit the Sun in elliptical paths, were revolutionary and helped explain the retrograde motion of Mars, a puzzling phenomenon that had perplexed astronomers for centuries. In 1609, Galileo Galilei became the first person to observe Mars through a telescope, a groundbreaking moment in both astronomy and science. Although Galileo's telescope was primitive by today's standards, his observations marked the beginning of telescopic astronomy and the modern study of planets. Galileo could not see much detail on Mars, but his work paved the way for other astronomers to use telescopes to study celestial bodies. In the decades that followed, telescopic observations of Mars advanced quickly. The Dutch astronomer Christiaan Huygens observed Mars through a more powerful telescope and became the first to sketch surface features. In 1659, he drew a dark region on Mars, which we now know as Syrtis Major, one of the planet's most prominent surface features. Huygens also recorded Mars' rotation, estimating that a day on Mars was similar in length to a day on Earth, a remarkable and surprisingly accurate observation. Around the same time, Italian astronomer Giovanni Cassini further refined observations of Mars, estimating its rotational period even more precisely. Cassini's measurements were incredibly close to the actual length of a Martian day, which is about 24 hours and 37 minutes. These early telescopic observations laid the groundwork for the detailed study of Mars, sparking an enduring interest in the planet that has continued into modern times. Mars has been a central figure in modern popular culture, captivating human imaginations for centuries. From early depictions in myth and literature to today's films, TV shows, and even music, the Red Planet has been portrayed in diverse ways, reflecting humanity's aspirations, fears, and curiosity about the unknown. In modern science fiction literature, Mars is often depicted as a mysterious, distant world ripe for exploration and colonization. Ray Bradbury's The Martian Chronicles, 1950, presents Mars as a place with its own ancient civilization, later colonized by humans, and explores complex themes such as imperialism, cultural clashes, and the consequences of human actions. This portrayal of Mars as a world with its own history and deep emotions contrasts with the more grounded survival narrative found in Andy Weir's The Martian, 2011, which was later adapted into a successful film in 2015. The Martian follows astronaut Mark Watney's fight for survival after being stranded on Mars, offering a scientifically plausible look at what it might take to survive on the red planet, emphasizing human ingenuity in teamwork. Both works contribute to the modern image of Mars as a site of challenge and potential, not just a barren wasteland. The portrayal of Mars in modern popular culture has significantly influenced public perception of space exploration. No longer just a mythic or distant object of fear, Mars has become a symbol of possibility, a place where humanity could one day establish a presence beyond Earth. Films like The Martian and TV shows like The Expanse have fueled the public's imagination about the potential for life on Mars and the challenges humanity would face in making it a home. As scientific advancements, such as NASA's Mars missions and the aspirations of private companies like SpaceX, push us closer to reaching Mars, the cultural representations of the planet continue to shape how we envision our future in space. Mars, once a symbol of danger and conflict, has transformed into a symbol of human resilience, hope, and the boundless possibilities of exploration. As we continue to look toward the stars, Mars remains a central figure in our collective imagination, shaping not just the way we dream about space, but also the way we approach the future of interplanetary exploration. Mars, commonly known as the Red Planet, is roughly half the size of Earth, with a diameter of approximately 6,779 kilometers. Its reddish appearance, visible even from Earth, comes from iron oxide, or rust, coating much of its surface, giving Mars a distinctive color against the night sky. This hue and unique features like vast plains, towering mountains, and expansive valleys have made Mars an object of fascination for centuries. Among Mars' most notable features is Olympus Mons, the largest volcano in the solar system, which rises nearly 22 kilometers high, around 3 times the height of Mount Everest. This colossal structure, covering an area the size of Arizona, hints at a past of volcanic activity that may have lasted for millions of years. Equally impressive is Valles Marineris, a canyon system stretching over 4,000 kilometers across the Martian surface. At points, this canyon system is 10 kilometers deep, far deeper and longer than Earth's Grand Canyon, suggesting Mars underwent significant geological changes early in its history. Mars' atmosphere, though thin, still plays a crucial role in shaping its environment. Composed mainly of carbon dioxide with traces of nitrogen and argon, this thin layer offers little insulation or protection from radiation and leads to extreme temperature fluctuations. Temperatures on Mars can range from a freezing -125 degrees Celsius in the polar regions during winter to around 20 degrees Celsius at midday near the equator in summer. However, without a dense atmosphere to hold in heat, temperatures can drop rapidly once the sun sets, making Mars a cold and challenging environment. Mars experiences seasons similar to Earth's due to its axial tilt of about 25 degrees. This tilt causes variations in temperature and weather patterns, including seasonal dust storms, some of which can grow into massive, planet-wide events lasting for weeks. These storms can obscure surface features and alter the landscape, temporarily reshaping Mars' appearance from above. Orbiting Mars are its 2 small, irregularly shaped moons, Phobos and Deimos. Their origins remain uncertain. Some scientists propose they were once asteroids captured by Mars' gravity, while others suggest they could be remnants of a larger object shattered by impact. Both moons add to the mysteries surrounding Mars and serve as potential sites for future exploration. Signs of ancient river valleys, lake beds, and polar ice caps on Mars suggest that liquid water once flowed across its surface. Today, water exists mainly as ice, especially at the poles, though recent evidence suggests there may be intermittent flows of briny liquid water. These features of Mars' landscape provide clues to a more temperate past, raising the possibility that Mars might have once supported life. These distinct physical characteristics make Mars one of the most intriguing planets for exploration, and understanding them is key to future human missions aimed at uncovering its secrets. The search for water on Mars has been one of the main goals of planetary science for decades, as water is essential for life as we know it. Observations from Earth hinted at a watery past, with what appeared to be ancient river channels and flood plains visible even in early telescopic images. Later, robotic missions provided more concrete evidence, uncovering clues to Mars' complex water history and transforming our understanding of the planet. In the 1970s, NASA's Viking missions were among the first to analyze Martian soil directly, suggesting that liquid water had once existed on Mars. Later missions, such as Mars Global Surveyor in the late 1990s, offered clearer evidence of dry riverbeds and valley networks, pointing to ancient, flowing rivers. Mars Odyssey, launched in 2001, detected significant amounts of hydrogen below the surface near the poles, suggesting the presence of water ice. The discovery of water ice was further confirmed by the Phoenix Mars lander in 2008, which dug into the soil near Mars' northern polar region and found water ice just below the surface. This discovery reinforced the idea that frozen water is abundant on Mars, especially near the poles. Meanwhile, Mars rovers like Spirit, Opportunity, and Curiosity continued to find minerals, such as clay and sulfate deposits, which form in the presence of water. These findings suggested that Mars once had standing bodies of water, possibly even lakes or shallow seas, and a more Earth-like climate in the distant past. In 2015, a significant breakthrough occurred when NASA announced evidence of recurring slope lineae, RSL, streaks on Martian slopes that appear to darken and fade with the seasons. These streaks indicated that liquid water might occasionally flow on the surface, albeit likely a briny, salty water that could remain liquid at the planet's freezing temperatures. This discovery fueled excitement about the possibility of present-day water activity on Mars, though questions remain about the exact nature and frequency of these flows. Most recently, data from the Mars Express orbiter suggested that a large lake of liquid water could exist beneath the ice at Mars' south pole. While this finding is still under investigation, it raises intriguing possibilities about the potential for microbial life existing in isolated pockets of liquid water beneath the surface. Future missions are being designed to explore these subsurface areas, as they could be some of the most promising sites to search for signs of life. The search for water on Mars continues to be a priority, as liquid water is crucial for the potential habitability of the planet. Every discovery of past or present water brings us closer to understanding the planet's climate history, its potential to support life, and its suitability for future human exploration. The search for life on Mars has fascinated scientists and the public alike for centuries. From early speculations about intelligent Martians to modern scientific studies, Mars has long been seen as the most likely place to find life beyond Earth. With its Earth-like seasons, polar ice caps, and evidence of ancient rivers and lakes, Mars holds many of the conditions that could potentially support life, at least in microbial form. NASA's Viking missions in the 1970s were the first to directly test for signs of life on Mars. Viking 1 and 2 were each of the experiments designed to detect biological activity in Martian soil samples. Although initial results showed some unexpected chemical reactions, the findings were ultimately inconclusive and did not confirm the presence of life. Despite this, Viking marked an important step, showing that Mars was chemically active and setting the stage for future missions. Over the years, Mars rovers and orbiters have expanded our knowledge of Mars' environment and its potential habitability. The Spirit and Opportunity rovers, which landed in 2004, found geological evidence of ancient water, such as mineral deposits formed in the presence of liquid water, reinforcing the theory that Mars once had the necessary conditions for life. The Curiosity rover, arriving in 2012, made a significant discovery when it detected organic molecules in Martian rocks. These carbon-based compounds are the basic building blocks of life, indicating that Mars has some of the raw materials necessary for life to exist or to have once existed. Although these findings alone are not proof of life, they suggest Mars could have supported simple, microbial life forms in the past. In 2015, scientists discovered recurring slope lineae, RSL, dark streaks on Martian slopes that appear and disappear with the seasons. These streaks may be caused by the flow of briny water, which remains liquid at Mars' frigid temperatures due to its high salt content. This discovery fueled excitement, as the presence of liquid water, even if temporary and salty, could create small habitable zones for microbes. The search for life on Mars gained new momentum with the detection of possible subsurface lakes at Mars' south pole. Using data from the Mars Express orbiter, scientists discovered areas beneath the polar ice cap that could contain liquid water, held in a liquid state by the pressure of overlying ice and high salt levels. These hidden reservoirs, protected from harsh surface conditions and radiation, could provide a more stable environment where life might persist if it ever emerged on Mars. The possibility of life in these deep, cold lakes is especially intriguing because they mirror similar extreme environments on Earth where microbial life thrives. In addition to water and organics, recent missions have been investigating methane on Mars. This gas, which can be produced by biological or geological processes, has been detected sporadically by orbiters and rovers. The presence of methane is tantalizing, as it could point to microbial activity below the surface, although non-biological processes could also explain the methane. With each new discovery, whether it's organic compounds, seasonal water flows, or potential underground lakes, the evidence for Mars' potential to support life grows. Future missions, like those planned by NASA, ESA, and private companies, aim to bring back Martian soil samples to Earth and to explore beneath the Martian surface, where conditions might be more favorable for microbial life. The quest to find life on Mars continues to inspire scientific exploration, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? Humanity's fascination with Mars has driven space agencies and scientists worldwide to send a series of missions aimed at exploring the red planet's mysteries. Starting in the 1960s, these missions have evolved from simple flybys to complex landers and rovers, each advancing our understanding of Mars' surface, atmosphere, and potential for life. The journey began with early flyby missions, such as NASA's Mariner 4 in 1965, which provided the first close-up images of Mars. These images revealed a cratered, seemingly barren landscape, shifting perceptions of Mars from a potentially Earth-like planet to a cold, rocky desert. Mariner 9, arriving in 1971, was the first spacecraft to orbit Mars and mapped nearly the entire planet, uncovering key features like Valles Marineris and evidence of ancient riverbeds. These findings hinted that Mars may have once had flowing water, sparking a new era of exploration focused on the search for life. The Viking missions in 1976 marked a significant leap forward, becoming the first to land on Mars and conduct direct experiments. Viking 1 and Viking 2 captured detailed images of the Martian surface and ran experiments to detect biological activity in the soil. Although inconclusive for life, Viking's soil analysis and atmospheric data laid crucial groundwork, confirming that Mars has seasons, weather patterns, and active geological processes. In the 1990s, a new wave of missions brought fresh insights. NASA's Mars Pathfinder, which deployed the Sojourner rover in 1997, demonstrated the success of rovers in exploring Mars. Its successor missions, Mars Global Surveyor and Mars Odyssey, provided critical information about Mars topography, climate, and the widespread presence of water ice below the surface. These missions set the stage for increasingly ambitious rover explorations. The 2000s saw the arrival of Spirit and Opportunity, twin rovers designed for a 90-day mission but lasting for years. Their discoveries transformed our understanding of Mars, as they found mineral and geological evidence that Mars had liquid water in the past, including signs of ancient lakes and possibly habitable environments. These findings reignited hopes of discovering life on Mars, past or present. In 2012, NASA's Curiosity rover landed in Gale Crater, equipped with advanced instruments to search for organic compounds and study Mars' climate and geology in depth. Curiosity's discovery of organic molecules in clay-rich areas indicated that Mars could have supported microbial life billions of years ago. The rover's ongoing mission continues to provide valuable data, revealing insights into Mars' atmosphere, soil composition, and potential habitability. More recently, the 2020s have seen a new level of exploration with the arrival of NASA's Perseverance rover and China's Tianwen-1 mission. Perseverance, landing in Jezero Crater, is searching for signs of ancient microbial life and collecting samples to be returned to Earth by future missions. This mission also introduced Ingenuity, a small helicopter that made the first powered flights on another planet, testing new technology for the aerial exploration of Mars. Meanwhile, Tianwen-1 marked China's successful entry into Mars exploration, contributing valuable data about Mars' surface and environment. These missions, driven by scientific curiosity and technological advancements, are unlocking Mars' secrets piece by piece. Every new mission brings us closer to understanding whether Mars was ever habitable and what it might mean for humanity's future on the Red Planet. The journey of Mars exploration is still in its early stages, with each mission building on the discoveries of the last, pushing the boundaries of knowledge and the possibilities for human exploration beyond Earth. The possibility of life on Mars has fueled scientific exploration for decades, inspiring countless missions and ongoing curiosity about whether the Red Planet might have once supported, or might still support, life. While early observers imagined intelligent Martians, modern science has shifted focus to microbial life, seeking signs of past or present biology in Mars' soil, rocks, and even beneath its surface. The first serious scientific search for life on Mars began with NASA's Viking missions in 1976. Vikings 1 and 2 each carried out a set of experiments to detect biological activity in the Martian soil. Although the results showed intriguing chemical reactions, they were ultimately inconclusive, with most scientists concluding that no definitive evidence of life was found. Despite this, the Viking missions provided valuable information about Mars' chemical environment and paved the way for more sophisticated studies in later missions. The Spirit and Opportunity rovers, which landed in 2004, uncovered geological evidence that Mars was once a warmer and wetter planet. They discovered minerals and rock formations, such as hematite spheres, which typically form in the presence of water. These findings suggested that Mars once had liquid water on its surface, an essential ingredient for life as we know it. By exploring Mars' surface, Spirit and Opportunity provided critical clues that the planet's ancient environment might have been more hospitable to life. The Curiosity rover, which landed in Gale Crater in 2012, took the search a step further. It discovered complex organic molecules, carbon-based compounds that are fundamental to life, in Martian rocks. These molecules hinted that Mars had not only water but also some of the building blocks of life. Curiosity also detected seasonal variations in methane, a gas that could be produced by biological processes. While methane can be created by geological activity, its presence on Mars added excitement as scientists speculated about the possibility of subsurface life contributing to these emissions. The potential for life on Mars gained more attention with the discovery of recurring slope lineae, RSL, dark streaks on Martian slopes that appear seasonally. These streaks could indicate flows of briny, salty water, which can stay liquid at Mars' low temperatures. Although the exact cause of RSL is still debated, this finding suggests that liquid water might occasionally flow on the Martian surface, creating a potential habitat for microbes in these extreme environments. In recent years, the discovery of possible subsurface lakes beneath Mars' south polar ice cap has further fueled the search for life. Using data from the Mars Express orbiter, scientists detected radar signals suggesting that liquid water may be trapped beneath layers of ice, where it could be insulated from Mars' harsh surface conditions. These isolated reservoirs, if confirmed, could offer the best chance for finding life, as microbes on Earth are known to thrive in similar cold, salty, and dark environments. NASA's Perseverance rover, landing in 2021, represents the latest chapter in Mars' search for life. Perseverance is exploring Jezero Crater, a site that once held an ancient lake and river delta, rich in clay deposits that could have preserved ancient microbial life. Equipped with the most advanced tools yet for analyzing rock samples and searching for biosignatures, Perseverance is collecting samples to be returned to Earth by future missions, where scientists will have the opportunity to study Martian materials in unprecedented detail. The search for life on Mars is not just about finding evidence of past or present organisms, it's also a quest to understand the conditions that made Mars habitable in its early history and to explore whether life, once sparked, could survive in extreme environments. Each mission adds a piece to the puzzle, bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? Whether or not Mars ever hosted life, the search will continue to inform our understanding of planetary habitability, offering insights that reach far beyond the red planet. The dream of reaching and eventually living on Mars has captivated humanity for generations, and modern advancements are bringing this vision closer to reality. With each mission to Mars, we learn more about the planet's environment, resources, and potential for sustaining human life. The coming decades promise a new era of Mars exploration, as space agencies and private companies work toward the ultimate goal of sending humans to Mars and establishing a long-term presence. The journey to Mars begins with robotic missions that lay the groundwork for human exploration. NASA's Perseverance rover, with its search for signs of ancient life and collection of Martian samples, is a key step in this process. The Mars Sample Return Mission, a joint effort by NASA and the European Space Agency (ESA), aims to bring these samples back to Earth in the 2030s, allowing scientists to study Mars' surface materials up close. These analyses will provide crucial information about the planet's geology, climate, and potential hazards, knowledge essential for human missions. Private companies like SpaceX are also central to the future of Mars exploration. SpaceX, led by Elon Musk, has an ambitious vision for human settlement on Mars. The company's Starship rocket, designed to be fully reusable, aims to transport cargo and eventually people to Mars, with the goal of establishing a self-sustaining colony. Musk envisions a future where humanity becomes a multiplanetary species, with a colony on Mars providing a backup for civilization. This ambitious vision has accelerated technological development, with SpaceX conducting frequent tests and advancing rocket designs that could make interplanetary travel more feasible and affordable. Preparing Mars for human habitation is a massive challenge. The planet's thin atmosphere, lack of breathable oxygen, and extreme cold make survival difficult. To address this, scientists and engineers are developing life support systems, habitat designs, and renewable energy solutions that could support human life on Mars. Potential habitats could include inflatable structures, 3D printed buildings made from Martian regolith, or even underground shelters to protect from radiation. Solar power, along with potential nuclear reactors, is being explored to provide energy in an environment where sunlight is weaker and intermittent due to dust storms. Another critical area of research is in situ resource utilization, ISRU, the concept of using Martian resources to support human missions. NASA's Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, currently being tested by the Perseverance rover, is a prototype designed to produce oxygen from Mars' carbon dioxide-rich atmosphere. A full-scale version of this technology could help produce breathable air for astronauts and create oxygen for rocket fuel, greatly reducing the need to transport resources from Earth. Mars exploration also requires strategies for addressing health risks. Mars' low gravity, high radiation levels, and isolation from Earth pose unique challenges for human health. Research is underway to develop protective suits, radiation-shielded habitats, and medical technologies tailored to these conditions. Studies on the International Space Station, ISS, help scientists understand how the human body adapts to low gravity and other space-related stresses, providing insights that will be essential for Mars missions. As these technologies advance, space agencies are preparing for the first human missions to Mars. NASA's Artemis program, which aims to return humans to the Moon by the mid-2020s, is viewed as a stepping stone to Mars. The Moon missions will allow astronauts to test equipment, refine long-duration mission protocols, and build skills that will be needed for Mars. If successful, NASA hopes to send humans to Mars in the 2030s, paving the way for longer-term habitation. The future of Mars exploration holds incredible potential. For scientists, Mars offers a chance to study a planet with a complex history, potentially similar to early Earth, and to answer questions about the origins of life. For explorers and dreamers, Mars represents a new frontier, a place where humanity can build a future among the stars. The next few decades will be a time of rapid advancement, and the prospect of a human presence on Mars is closer than ever. With each step forward, Mars becomes not just a distant world but a potential second home, marking the beginning of a new chapter in human exploration and the journey toward becoming a space-faring civilization.